Welcome to Math with Professor V. In this video, I'll be solving the most recent exam that my Calculus 2 class took, spring 2025. It covered areas between curves, volumes by cross-sections, slicing, and cylindrical shells, work, and then integration techniques, only including integration by parts and trig integrals. Trig sub, partial fractions, all that stuff is going to be on the next exam. Okay, let's jump right in. 10 questions. Find the area enclosed by the given curves. You must include a neatly labeled sketch of the curves and region. And we have x equals 2y squared and x equals 4 plus y squared. So hopefully, based on some pre-calc and previous math knowledge, you guys can recognize that both of these are parabolas opening to the right, since we have x as a function of y. First thing, to get a nice graph going, we need to find the intersection of these two curves. So we're going to do that by setting them equal to each other. So we have 2y squared equals 4 plus y squared. So now I'll move that y squared from the right over to the other side, and then we just have y squared equals 4, which means y equals plus or minus 2. And then substituting that into either of the equations, we get that x is equal to 8. So that is where the two curves intersect. All right, sounds good. If you need more points, you can go ahead and make a table. Some of my students did. If I look though, x equals 2y squared, the vertex of that parabola is just going to be at the origin, 0, 0. And then the vertex of this parabola is going to be at 4, 0. And I feel confident that that's going to be enough for me to draw a graph. But if you need more, you do you live your life. So we're going to go up to positive 2, down to negative 2 in the y direction. And then here's 4, here's 8. Okay, those are the interesting points. And then we've got 8, 2, 8, negative 2. That's where they intersect. Let's graph x equals 2y squared. That one has the vertex at the origin. And then our other parabola has vertex at 4, 0, and it's going to intersect, so it's going to go through 8 plus or minus 2 as well. And who is this? This is x equals 4 plus y squared. Okay, so this is the region whose area we're trying to find. Let's shade it in. And then we have to decide, are we going to integrate with respect to x or with respect to y? And maybe based on the way the equations were given, since they're functions of y, you're already feeling like, yeah, we're going to integrate with respect to y. And that's true, because remember, when we find the area between two curves, it's basically the same setup as when you found the area under a curve. You're just determining the height by taking top function minus bottom function or right function minus left. And we're stacking rectangles. And these rectangles stack more nicely in the y direction. So the base right here, that's delta y. And then the height of the rectangle is going to be given by function on the right minus function on the left. Who's on the right? Bounding the height, it's 4 plus y squared. And then who's on the left? It's 2y squared. So this gives us 4 minus y squared. That's the height of the rectangle. If you tried to integrate with respect to x, you would have to stack your rectangles this way. Then you would have to solve each of these for y in terms of x. You'd have plus or minus square root. It would be messy. I don't recommend. Okay? Now, in order to find the area, we have to set up a definite integral. Since we decided we're integrating with respect to y, the limits need to match where the area is bounded in terms of y. So notice the area begins, this region begins when y is negative 2, all the way up until positive 2. So those are our limits of integration, negative 2 to 2. And then we know to find area, we take base times height. Base is just delta y, which becomes dy, and the height we found already, 4 minus y squared. Okay. Now we just have to integrate. This is a relaxing little polynomial. One thing we can do though to make our life easier is notice this region is symmetric with respect to the x-axis. So that means I can actually double the value of this integral and only go from 0 to 2, which is fabulous because who doesn't love it when the lower limit's 0? It makes life so nice. All right. And then from here, we can just start integrating term by term. Keep that 2 outside, minding its business. Antiderivative of 4 is 4y minus, this is going to be 1/3 y cubed from 0 to 2. Again, keep the 2 outside, excuse me. And then this is going to be 4 times 2, 8, minus 8/3 minus 0. This was unnecessary. Okay. 8 minus 8/3, so that's 24/3 minus 8/3. That's 16/3 times 2, 32/3, and we are done. Okay. First problem, most of them did perfectly well. I think the only issue was some people had the incorrect limits of integration and put them in terms of x, even though this integral is in terms of y, so the limits need to be in terms of y as well. Everything has to be matchy-matchy. Okay, next problem, use the disk washer method. So I'm telling them the method to find the volume of the solid generated by revolving the region about the x-axis. You must include a neatly labeled sketch of the region and a typical disk or washer. Okay, so we have two functions, y equals negative 3x plus 6, y equals 3x, and x equals 0, all bounding the region. Again, let's find the intersection. So I'm going to set negative 3x plus 6 equal to 3x. So I get 6 is equal to 6x, so x equals 1. And if x is 1, then the y value is 3. So these two curves, they're actually linear functions, so they're not curves, they're lines. They intersect at 1, 3. And they're lines, so we should be able to graph them without having to make a table, yes? I would certainly hope so. If I look at the first one, the y-intercept is at 0, 6. Okay, good. And I know all the action's happening when x is 1, so you don't have to go too far out on the x-axis. And then I'll label this up to 6, and I'll call this 3, you know? It's your graph, so scale it in a way that's going to be convenient for you so that you can see what's going on. I spread this out because if I put the 1 here, the region's going to look so teeny tiny that it'll be difficult to identify outer radius, inner radius, what's going on. So you don't have to scale x and y the same, right? Okay. So we have, let me graph this guy, negative 3x plus 6. So it's going to go through 0, 6, and then 1, 3. It'll keep going, but this is the only part that's interesting to me for our purposes. So y equals negative 3x plus 6 is right there. And then y equals 3x, intercept is 0, 0. And then it also goes through 1, 3. And then x equals 0. Well, don't forget that's the y-axis. So right here, this is also bounding the region. Let me just darken it. Can you see what the region is then that we're spinning? We're spinning this triangular region. And we're spinning it where? About the x-axis. We're spinning it about the x-axis. So when we spin it, it's going to reflect. Okay. And then we're going to draw a typical, in this case, we'll have a washer because there's a hole in the middle. Let me do it with a darker colored pen. There's my washer. Okay. We have to identify the outer radius and the inner radius because there's 2 in this case. So big R and little r. First and foremost, are we integrating with respect to x or y? Well, I'm spinning around the x-axis. When we do the disk or washer method, we slice perpendicular to the axis of revolution and see how these slices move in the x direction. Slice, 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 slice. I'm moving in the x direction, so we will be integrating with respect to x. Okay, which is good. We already have our equations as functions of x. Outer radius, big R, goes from axis of revolution to that outer function. To figure out an expression for big R, you take top minus bottom. Who is bounding big R on the top? Y equals negative 3x plus 6. Who's bounding on the bottom? This is just y equals 0. Negative 3x plus 6 minus 0. I'm not going to write the minus 0. Little r, where is little r? Little r is from where we're revolving to the edge of the inner radius. Again, to find an expression for little r, you do top function minus bottom function. This is little r right here. Who's bounding little r on the top? 3x. Y equals 3x. Who's bounding it on the bottom? Y equals 0. So 3x minus 0. I'm not going to write the minus 0. And then there we go. We're ready to set up our integral. We already established we're integrating with respect to x. So volume's going to be pi. For washers, we have pi, big R squared minus little r squared. Limits of integration need to be for x. Everything must be matchy-matchy. So you look at your graph and you go, the original region was bounded in terms of x from x equals 0 to x equals 1. So those are my limits. Then you have big R squared minus little r squared. Good? Okay. Then from here, you just have to be careful. Some students messed up because they did not FOIL and clean up correctly. So this is pi times the integral 0 to 1. Negative 3x plus 6 quantity squared will be 9x squared minus 18x times 2. So minus 36x plus 36 minus 3x quantity squared is 9x squared dx. You have to square the 3 and the x. Now the 9x squareds cancel. I can also factor out a 36 just to make life nicer. So we have 36 pi sitting outside. Integral from 0 to 1. This is going to be negative x plus 1, aka 1 minus x. That looks cuter, dx. And then now we can integrate this, no big deal. 36 pi x minus 1/2 x squared from 0 to 1. This is 36 pi times 1 minus 1/2 minus 0. So this is all a half times 36 pi, 18 pi. All right, very good. Moving on. Use the shell method to find the volume of the solid generated by revolving the enclosed region about the indicated line. Include a sketch of a typical shell and label its relevant parts. So we're spinning this enclosed region right here about the line. Do you see what it says? About the line y equals 1. So here's y equals 1. We're spinning it around y equals 1. So it's going to reflect like this. Okay. And we're using the shell method. Okay. So when you use the shell method, you peel parallel to the axis of revolution. You peel parallel to the axis of revolution. So I'm peeling in the y direction. So I'm going to integrate with respect to y. Now I need to draw a typical shell. So in order to do that, you look, okay, I spun around y equals 1. That's a horizontal line. So you come to your original region and you draw a baby horizontal line segment that is bounded by the region. It has to go through the entire region, no more, no less. Then you reflect it over on the other side, and then you make your cylindrical shell. Boom, boom. This is the height of your cylindrical shell, and this right here is the radius. Okay, so when we're doing volumes by shell, we have volume equals 2 pi. We'll go from C to D, R times H, and in this case, it's dy. Okay, so let's identify the radius and the height. The radius will never involve the functions that bound the region. That's for the height exclusively. The radius, if you're integrating with respect to y, will be plain old y, Or if you're spinning around some other line, then it might be y plus some number or some number minus y, etc. But you'll never include the functions. It won't have, radius will not have 6y squared or 6 cubed root of y for the shell method. That's all captured in the height. So look at the radius here. We will zoom. Here's the radius. We're going to do what's bounding it on the top minus bottom. This is y equals 1. So 1 minus whatever the y value is, where we're peeling, is the radius. Radius is 1 minus y. Now what about the height? Again, we're going to do right minus left. On the right is the solid function, 6 cubed root of y. On the left is the dashed function, 6y squared. So 6 cubed root of y minus 6y squared. Right minus left. And I have more in-depth video lectures on all these topics linked in the description. I'm not going through super basic slow right now like I would when I lecture. So if you need more in-depth, breakdown, go watch those videos. Okay, we're ready. Let's set her up. So volume's going to be 2 pi. Now the limits, again, have to be in terms of y based on the original region. The original region was bounded from y equals 0 to 1. And then we have radius times height. 1 minus y times 6. Ugliest 6 I've written in my life. 6 cubed root of y is y to the 1/3 minus 6y squared. I'm getting ready because we're going to integrate. Okay. Now what we can do, we can factor this 6 out and put it with the 2 pi in the front. So then we have 12 pi integral 0 to 1. 1 minus y to the 1/3 minus y squared dy, and then you just FOIL your little heart out. So 12 pi integral 0 to 1, y to the 1/3 minus y squared minus y to the 4/3 minus y cubed dy. And then just go term by term, add 1 to each exponent, divide by the new exponent. So this will be 3/4 y to the 4/3 minus 1/3 y cubed minus 3/7 y to the 7/3. You know what? This should have been a plus. Excuse me. Were you screaming at me through the screen? Good. 1/4 y to the 4th from 0 to 1. Okay, beautiful. And then thank heavens the limits are 0 to 1. I mean, would you want to take the 7/3 root of anything else? Surely no. Okay, so we've got 12 pi times 3/4 minus 1/3 minus 3/7 plus 1/4 minus a bunch of zeros. So let's see. Oh, this is nice because we've got 3/4 plus a 4th. So that's 1, right? So we've got 12 pi times 1 minus 1/3 minus 3/7. Common denominator on these guys is 21. So that's 21 over 21 minus 7 minus 9. So we'll have 5 over 21. So 12 pi times 5 over 21. And then those I can reduce, divide by 3, 4, 7. So then this is, yes, 20 pi over 7. Voila. Okay. Very good. Very good. All right, let's move on to some work problems. Solve the following problem. The base of a rectangular tank measures 4 feet by 5 feet. The tank is 6 feet tall, and the top is 4 feet below ground level. The tank is full of water, weighing 20 pounds per foot cubed. How much work does it take to empty the tank by pumping the water to ground level? Give your answer to the nearest foot pound. Ooh, okay, here we go. So I have a whole video on how to find the work when pumping liquid from containers. Sounds oddly specific, but it's what we study. It needs to be done. Let's get a diagram down so we can see what's going on. We've got a rectangular tank, They gave us some dimensions. I'm not promising to draw it to scale, but I will label it correctly. How about that? Okay. It is 4 feet by 5 feet. 4 feet, 5 feet, and it's 6 feet tall. And then the top is another 4 feet below ground level. Yes. 4 feet there. This is the ground. And it is full of water. It's full to the brim. Full, full, full. They gave me the weight density of water. Okay. How much work does it take to empty the tank by pumping the water to ground level? Give your answer to the nearest foot-pound. So I'm just going to work through the solution. If you need the lecture, then just go watch the video that I have linked in the description. First thing is I want the volume of some arbitrary slice of water in the tank, which we call V sub I. And we know if we were to slice up, I know you can't really slice water, but we're pretending that's how we compute things in calculus. We slice them up, we approximate, then we take infinitely many in a limit, and there we go. Then it's not approximate anymore. So pretend you can slice water in its liquid state. Here's my little slice. Got it? Okay. Somewhat therapeutic actually drawing this for you all. There's my slice. Okay. What shape is it? It's just a little rectangle. So that's length times width times height. So length and width are 4 and 5. And then the height is delta y, the height of the slice. Okay. So V sub I is 20 delta y. You don't use the height of the whole tank. I'm not computing the volume of the whole tank. I'm computing the volume on the slice. Then what do I want to know? I want to know what is the force required to lift one slice or one layer of water. Well, that's why they gave me the weight density right there. So we have that it's 20 pounds per foot cubed. And what I didn't write was that the volume over here, the units on it, are feet cubed for one slice. So if I take the force required to lift one slice and multiply it by 20 delta y feet cubed, which is over 1, then notice my units feet cubed cancel. Perfect. And then that's going to give me a quantity that is in pounds, which is force. So that's the force required to lift one slice. Then I want to know what's the distance each slice needs to move to be out of the tank. Well, how are we partitioning things? I'm going to call this height y equals 0. This is the height y equals 6. Up here is y equals 10. Okay? And then this is maybe halfway through the tank, y equals 3, 4, 5, etc., right? Okay, so the layer that's at y equals 0, it has to move a full 10 feet until it's out of the tank. The layer that's at y equals 1, it would move 9 feet to be out of the tank. The layer at the top has to move 4 feet to be out of the tank. So the distance each slice moves based on its height y is 10 minus y. All right, now we're going to put it all together. So the work is equal to integral of force applied to each slice times distance. And in the integral, this delta y becomes dy. So we'll have 400 times 10 minus y dy, not delta y. Now the limits of integration are what you have to actually apply work to. And so notice we're only applying work, where is there water, from y equals 0 to 6. There's no water from 6 to 10, so no force is being applied to anything in this region. So the limits of integration should go y equals 0 to 6. Watch out for that. Okay, now we integrate. Take that 400 out. Integral 0 to 6, 10 minus y dy. So that's 400 times 10y minus 1/2 y squared, evaluated from 0 to 6. So this is going to be 400 times 60 minus 18, 400 times 42, which is 16,800, and the units on this are foot-pounds, not joules. We were in the imperial system. Get it right. I have a video coming out soon on math mistakes that cost millions of dollars, and unit conversion is one thing that is very key that I discuss in there. Okay, how are we doing? Good, let's move on. Next example. Given f of x equals x minus 3 squared on the interval from 2 to 5, find the average value of the function over the given interval. So formula for average value is 1 over b minus a times definite integral a to b f of x dx. So this will be 1 over 5 minus 2 is 3. Integrate from 2 to 5, x minus 3 squared dx. Now don't multiply this out. It's so much easier to integrate if you just leave it factored as x minus 3 quantity squared. You don't even need to use sub because there's no coefficient in front of the variable x. So this will be 1/3. Antiderivative of something squared is that something cubed, and then I need a 1/3 in front, evaluated from 2 to 5. That's how to integrate like a boss. And then you've got 1/9. 5 minus 3 cubed, that's 2 cubed. Minus 2 minus 3 cubed, that's negative 1 cubed. So that's 8 plus 1, that's 9. 1/9 times 9 is 1. So average value is 1. Part B, find C such that f of C equals the average value of the function. So we set f of C equal to the average value 1. F of C is C minus 3 squared. Use the square root property, so we get C minus 3 is plus or minus 1. So many forgot the plus or minus. It was sad. So C equals negative 1 plus 3, which is 2, and 1 plus 3, which is 4. And then sketch a graph of f and a rectangle whose area is the same as the area under the graph of f. Your graph must be neat and labeled precisely. So we're only graphing f on the interval that was given from 2 to 4. It's a parabola, and I can tell it's been shifted 3 units to the right. So the vertex is at 3, 0. And then if I plug in 2, y will be 1. And if I plug in 4, it will also be 1. Oh, we got to go all the way to 5. What am I saying? We're going to 5, guys. Oh, we're going to 5, guys. We're not. Not today. 5 minus 3, so 5. This will be 4. Okay, perfect. And then the average value tells me what the height of the rectangle needs to be. Since the average value was 1, that's how tall my rectangle is going to be on this interval. Okay, so we'll go up to 1, 2, 3, 4. 1, 2, 3, 4, 5. Perfect. So at 2, my y value is 1. At 3, it's 0. At 4, it's 1. And at 5, it's 4. So here's the parabola. And then f average was equal to 1. So that's the height of the rectangle on the same interval. This is f average. Same base. Here's my rectangle. Good. Now the area inside this rectangle, let me color it purple so it's all matchy and beautiful. The area inside this rectangle is the same as the area underneath the curve on the interval. Yes. Because the average value tells us the average height of the function. So the average height of this parabola on the interval is 1. Good? That's literally all there was to it. Easy peasy. Okay, the rest of the exam was integration. So evaluate the following integral from 0 to pi over 2, cosine squared 3x times sine cubed 3x dx. Whenever you have a product of sines and cosines, if one of them is odd, you want to pull the odd man out. So we want to rewrite this as integral 0 to pi over 2 cosine squared 3x times sine squared 3x times sine 3x dx. The whole point is you want this odd man to be absorbed and become du when we make our u substitution. So then just think backwards. If du is going to involve sine 3x, what would u need to be? Yes, u would need to be cosine 3x. 3x and not cosine squared. So let's see, du would be, don't forget the chain rule, that's where many students messed up, -3 sine 3x dx. And look, all I've got right here is sine 3x dx. So we're going to divide by this -3, -1/3 du is sine 3x dx. In order to make the u sub, I'm going to need to think of sine squared x in terms of cosine, right? Because u is cosine 3x, so that's u squared. This will be my -1/3 du. I got to get rid of this. So I'm going to rewrite that as 1 minus cosine squared 3x. And then we should be pretty much set up for success. You know what I'm saying? Oh, good. Now, make sure you change your limits of integration immediately. ASAP, like a dirty diaper. You're not going to let that fester, okay? Once your integral has u's in it, everything must be matchy-matchy. Don't mix x's and u's simultaneously. You're not in multivariable calc. And then also, these limits belong to the original variable in the integral x. So once you have u's in the integral, we got to change them. So the limits are also in terms of u. So let's see here. These limits are x limits. I'm going to plug them in for x here, where I made my u sub. So u of 0 is cosine of 3 times 0, which is 1. And then u of pi over 2 is cosine of 3 pi over 2, which is 0. Okay, so now we can rewrite the integral all in terms of u. We're going to have new lower limit 0 becomes 1. New upper limit pi over 2 becomes 0. Cosine squared is u squared. 1 minus cosine squared 3x is 1 minus u squared. And then sine 3x dx is -1/3 du. I'll put the -1/3 out there. Okay? And then from here, you should be home free. The worst is over. So flip those limits and make it positive, right? Aren't you dying to do that? Go 0 to 1, and now that negative is gone in front of the 1/3. Oh, I feel better already. And then distribute the u squared minus u to the 4th du. And then, oh, what a relaxing antiderivative. We earned it. We've been stressed. Look at this. Beautiful, beautiful. 1/3 u cubed minus 1/5 u to the 5th, 0 to 1. So this is 1/3 times 1/3 minus 1/5 minus 0. 1/3 times 2/15 is 2/45. Done. Boxed and moving on with our lives. This one we practiced extensively in class. Definite integral 0 to 1, y times tan inverse of y dy. We need to do by parts. U dv. U has to be tan inverse of y because we don't know its antiderivative. So dv must be y dy. Du, derivative of tan inverse of y is 1/1 plus y squared dy. And then antiderivative of y would be 1/2 y squared. Okay, now we use our by parts formula. So this is going to equal uv 1/2 y squared tan inverse of y evaluated from 0 to 1 minus integral, still 0 to 1, of v du. I'm going to take the 1/2 outside, and then you'd have y squared over 1 plus y squared dy. Good? Okay. Now focus on this integral. No u sub will save you because this is not y to the first up here. It's not 1 degree lower. So you could long divide, but what's much easier is if you add and subtract 1 in the numerator. And you might say, Professor V, why would you do such a thing? Well, I really want to rewrite the integrand so that I can take its antiderivative. And if I add and subtract 1, now I have y squared plus 1 over 1 plus y squared minus 1 over 1 plus y squared dy. Good? Are you happier? Do you see the light at the end of the tunnel? Not yet? Oh no. I want to point out this portion here, the UV, you have to write that it's evaluated from 0 to 1 until you evaluate it. So don't forget that. Minus 1/2 integral 0 to 1. This is 1 minus, you should know antiderivative now of the integrand. Yes? Antiderivative of 1, we know that. Antiderivative 1 over 1 plus y squared, tan inverse of y. Hooray, we've made it. We just got to keep it together and not screw up when we evaluate everything at the limits of integration. Now, I'm not going to write this anymore because I'm going to take antiderivative and put a big old 0 to 1 at the end. That's allowed at this step. Minus 1/2 antiderivative of 1 is y plus 1/2 tan inverse of y from 0 to 1. Don't have a panic attack. All I did was distribute the negative 1/2 whilst integrating. Good? That was fancy. I know. Why don't we take the 1/2 out? I mean, is it doing anything for you? I'm not happy about it. Okay, now we can plug in our limits of integration. 1 squared tan inverse of 1 minus 1 plus tan inverse of 1, upper limit, minus 0 minus 0 plus tan inverse of 0. Cute. Tan inverse of 1 is pi over 4. Pi over 4. That just stays negative 1. Love it. And then this is just a bunch of zeros. And we've got a 1/2. So 2 pi over 4 is pi over 2 minus 1. So this becomes pi over 4 minus 1/2. Okay. Good. They've practiced this one in class. I did it for them. I made them do it for classwork. I made them do it for their review. So the ones who practiced, they knocked it out of the park. The ones who didn't, it didn't quite come together. Okay, evaluate the integral. This one also was a classwork problem. It is, I'm going to take the 1/2 out. E raised to the square root of 5x plus 10 dx. This one requires a substitution and then integration by parts. So because of that, I'm going to save the variable u to do integration by parts, and we'll make a t substitution. Let's let t be the exponent. So let t be the square root of 5x plus 10. Square both sides, so t squared equals 5x plus 10. And now differentiate. It's so much cleaner. 2t dt equals 5 dx. All I have is lonely little dx, so I'm going to get it by itself. So 2/5 t dt equals dx. And we are ready to make our substitution. It may not feel like it, but we are. 1/2 stays outside. You have e raised to the t now, and instead of dx, you have 2/5 t dt. And then look, the 1/2 and the 2 cancel, and this is just the cutest little integral you ever did see. 1/5 integral t e to the t dt. You can do traditional by parts here. You can do tabular here. You just live your best life. I really love tabular so very much, but I'll do traditional because the last problem requires tabular. So u is going to be t, not the other way around. dv is e to the t dt. So du is dt, and v is just e to the t. Keep that 1/5 outside, okay? And then we've got uv, so that's t e to the t, minus integral v du e to the t dt. Boom. And then we're done. Antiderivative of e to the t, fan favorite, t e to the t minus e to the t plus c. I can factor out e to the t, can't I? Yes. Always simplify completely. And then don't forget to go back and substitute in. T was the square root of 5x plus 10. So this is e raised to the square root of 5x plus 10 over 5 times square root 5x plus 10 minus 1 plus c. Boom. Voila. It needed to be factored to be considered completely simplified and 100% correct. Okay. 2 more to go. The class has a couple hours to do the exam, and I usually make the key after I write it in under 10 minutes. So I know I'm going quickly, but I figure you guys are just watching this for review purposes. Like I said, if you want it broken down, I got other videos for that. Evaluate the integral. Tangent to the 4th t times secant to the 6th t dt. Since I have an even power on secant, easiest thing is to break off secant squared and then u sub and let u be tangent t, okay? Let's do the prep work first though. Let's rewrite it so we're ready to roll. So this is tangent to the 4th t times secant to the 4th t times secant squared t dt. So this is basically going to be my du. Then think backwards. Who does u need to be? Well, u would be tangent t. Then du would be secant squared t dt like I want. Perfect. And then you can see here, this tangent to the 4th, that would be u to the 4th. But what about secant to the 4th t? Well, this is where you use your Pythagorean identity and you go secant to the 4th t, that's secant squared t squared. And secant squared I could write as tan squared t plus 1. And then all of that is squared. So this is going to become u squared plus 1 squared. And no funky constants or anything to contend with. Look how relaxing. So this is u to the 4th, u squared plus 1 squared du. Are we good? Okay, FOIL out u squared plus 1. So this is u to the 4th times u to the 4th plus 2u squared plus 1 du. And then distribute. So that's u to the 8th plus 2u to the 6th plus u to the 4th du. And then anti-differentiate term by term. 2/7 u to the 7th plus 1/5 u to the 5th plus c. And then go back. U was tangent t, so 1/9 tangent to the 9th t plus 2/7 tan to the 7th t plus 1/5 tan to the 5th t plus c. Okay, only one more to go, and I'll leave to go to hot yoga. We finished in perfect timing. Couldn't have done it better. All right, x cubed times cosine 4x dx, antiderivative of all that. It would take multiple rounds of integration by parts, or let's do the tabular method. We can get it done in no time. I have to tell you guys, I didn't appreciate tabular method until I got to differential equations, because you do a lot of integration by parts over and over and over in the same problem. It's really, really worth mastering, okay? DI method, tabular, whatever you want to call it. You put the polynomial, whoever's derivative is going to go to 0 in the D column, which is what you would pick u to be, right, when you do by parts normally. And then you're going to integrate or anti-differentiate cosine 4x. So start on the left, take the derivative until you get 0 of that function. So one derivative is 3x squared, 6x, 6, 0. So that's how many times I have to anti-differentiate. Then we have 1/4 sine 4x. Keep taking anti-derivatives. Negative 1/16 cosine 4x. Negative 1/64 sine 4x. And positive 1/256 cosine 4x. Then we take diagonal products. Always left column to right column, one row down, and then the sign alternates. So the first one, don't change the sign, then add an extra negative and always alternate. And then we're pretty much done. So we got 1/4 x cubed sine 4x. The next one's going to be plus because you have minus and another minus. So plus 3/16 x squared cosine 4x minus, because you have a plus and a minus, 6/64, that reduces to 3/32 x sine 4x minus 6/256, it reduces to 3/128 cosine 4x plus c. X cubed, x squared, x nothing. Perfect, and we're done. Okay, I think some people just forgot to reduce, or they forgot x squared. They were just sloppy, which, you know, will cost you. It will cost you in school, in life, in so many ways. That concludes the exam solutions. It was fast and furious, you know. I like to do math fast because it's fun for me. This was just a quick work through. I hope that you were able to solve all of these problems. And then if not, then just go back, watch the video lectures and see whatever gaps you need to fill in. Like I said, I give them a couple hours to do this exam, but I mean, most students, if you have like a really good mastery, should be able to finish in about half that time. All right. Don't forget to give the video a thumbs up. Subscribe if you haven't already. Follow me on Instagram and TikTok. Like I said, I have some exciting new content coming soon. And I am off to hot yoga. I hope everyone has a beautiful day, and I'll be back sooner than later. Bye.